Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera and good day to everyone. I am Yusuf Hamdani bin Jalaluddin from School of Management, Industry Science Malaysia, one of your lecturer for Business Statistics course. Today I'm going to walk you through chapter 9, and it is about the fundamentals of hypothesis testing for one sample test. One sample test refers to testing one population parameter. And here are the objectives of chapter 9. In this chapter, you learn number one, the basic principles of hypothesis testing. Number two, you learn some possible errors in hypothesis testing. Number three, you learn how to use hypothesis testing to test a mean when the population standard deviation is known, denoted by sigma, and when the population standard deviation is unknown. And finally, learn how to use hypothesis testing to test a proportion, denoted by symbol pi. I'm going to divide my presentation into three different parts, and this is going to be the first part. Hypothesis testing is a big topic. It starts from chapter 9 to chapter 13. So there are 5 chapters that discuss materials related to hypothesis testing. And hypothesis testing is grouped under inferential statistics. And inferential statistics is a branch of a bigger group called statistics. And from the previous chapters, we know that inferential statistics are methods that use data collected from a small group, that is sample, to reach conclusions about a larger group, that is population. So we study, in inferential statistics, we study a population using samples from the population. And there is another topics that is under inferential statistics called estimation, and we have discussed this topic in chapter 8. And beside inferential statistics, there is another branch of statistics that is called descriptive statistics, and it's defined as methods to summarize and present data. And you have been exposed to descriptive statistics in chapter 2 and chapter 3. Now let's take a look at what is a hypothesis. So we can define hypothesis as a claim or a belief assertion about a population parameter. So hypothesis is a claim or a belief about a population parameter. So parameters is defined as a value that describes a characteristics of entire population, such as mean, proportion, variance, standard deviation, etc. So here we have an example, population mean, and also a population proportion. Then we have to write a hypothesis based on population mean. Here is an example. A mean monthly cell phone bills in the city is equal to RM42. So we use symbol mu to represent population mean equal to RM42. For the population proportion, we have another example. The proportion of adults in the city with cell phones is equal to 0.88. We use symbol pi to represent population proportion. Hypothesis and hypothesis testings. Hypothesis actually is a statement about the value of a population parameter developed for the purpose of testing. So hypothesis actually is a statement. So you have to write your hypothesis. The hypothesis must be related to a value of a population parameter. and we need to test the hypothesis. Another example of hypothesis is 20% of all customers at Subaidah restaurant USM return for another meal within a month. So this is actually 20% refers to population proportion. So what is hypothesis testing? Hypothesis testing is a procedure based on a sample with sample evidence and probability theory to determine whether the hypothesis is a reasonable statement. So hypothesis testing consists of a set of procedures to test whether the hypothesis is a reasonable statement. Here is some steps in hypothesis testing. Step number 1 to step number 6. Step number 1, state null and alternate hypothesis. Step number 2, select a significance level. Step number 3, identify the test statistics. Step number 4, formulate a decision rule. Step number 5, calculate the calculated value and make a decision and conclusion whether to reject or not to reject the null hypothesis. And the final step, that is step number 6, is to make a conclusion based on your decision. And there are two types of hypothesis. Hypothesis number 1 is null hypothesis, and number 2 is alternative hypothesis. The null hypothesis is denoted as H sub 0. Sometimes people might call it as H naught. H naught. Null hypothesis states the claim or assertion to be tested. Example, the mean diameter of a manufactured bulb is 30 millimeter, and we use the symbol H sub 0 colon mu is equal to 30. So that is the symbol for null hypothesis. That's how we write our null hypothesis as an example. And it is always about population parameter. Always about population parameter and not about a sample statistic. Please remember this. This is very important. Null hypothesis is always about a population parameter. So for example, H sub 0 mu is equal to 30. So that is the null hypothesis, the correct null hypothesis. But if you use sample statistics such as X bar to represent the sample mean equal to 30 for your null hypothesis, and that is not the correct way. So never use sample statistics for your null hypothesis. So null hypothesis begin with the assumption that the null hypothesis is always true. And null hypothesis is true. This is very similar to the notion of innocent until proven guilty. So if you take somebody to court, the OKT or the accused person is not guilty until proven. So it's also null hypothesis also refers to the status quo. The status quo represent the current. It also represent the current belief in a situation. The current belief in a situation may represent the current belief of majority of people. So majority of people believe the null hypothesis is true. And always always contains equality, equal sign, equal to, less than or equal to, or greater than equal to. So your null hypothesis must always contain equal sign. For example, you have a null hypothesis mu equal to 30. Another example, mu is less than or equal to 30. Mu greater than or equal to 30. So here in these three cases, we have equal sign for every null hypothesis. So don't forget, always use equal sign for your null hypothesis. So your null hypothesis may or may not be rejected. Okay, let's take a look at the alternative hypothesis denoted by H sub 1. You can also use H sub A to represent alternative hypothesis. The letter A actually represent the word alternative. So alternative hypothesis is the opposite of the null hypothesis. Example, the mean diameter of a manufactured bulb is not equal to 30 millimeter. Then we write our alternative hypothesis as H sub 1 colon mu not equal to 30, and then from our previous null hypothesis stated as H sub 0 colon mu equal to 30. So here we use the symbol equal sign, equal for our null hypothesis and not equal to for our alternative hypothesis. So the symbol that we use for alternate and the null are opposite of each other. The alternative hypothesis challenges the status quo, challenges the null hypothesis. So status quo refers to null hypothesis, always challenges the null hypothesis. And alternative hypothesis never contains the sign equality. These three signs should not be used for the alternative hypothesis: equal to, less than or equal to, or greater than or equal to. So here, three possible signs that we can use for our alternative hypothesis. The first one is mu not equal to 30. Second is mu less than 30. And also the last one, the last symbol we can use for our alternative hypothesis is greater than. So we use not equal to, less than, or greater than for the alternative hypothesis. And the alternative hypothesis may or may not be proven. So it is generally the hypothesis that the researcher is trying to prove. So alternative hypothesis is also known as researcher's hypothesis. And when you conduct a study and you write your hypothesis should represent the alternative hypothesis. Let's take a look at the overview of the hypothesis testing process. As mentioned just now, null hypothesis represent a claim about the population parameter. So here we have a statement that the population mean age is 50, and we write our null hypothesis and alternative hypothesis. Mu equal to 50 as null, mu not equal to 50 as our alternative hypothesis. And after we have written our hypothesis, we need to sample the population and find the sample mean. Suppose the sample mean age was 20. So x bar is equal to 20. That is significantly lower than the claimed mean population age of 50. So 20 is very much lower than the population age of 50. So if the null hypothesis were true, the probability of getting such a different sample mean would be very small. So chance of getting a true null hypothesis will be very small, and because of that we have to reject the null hypothesis. In other words, getting a sample mean of 20 is so unlikely if the population mean was 50. So we conclude that the population mean must not be 50. That is based on our sample mean. So we can draw a distribution to represent our problem. So this is we use a normal distribution to represent the problem, where we use the mean of the population 50 at the center of the distribution, and when we plot our sample mean, which is to the left of 50, very far from the center, and from this we observe that it is unlikely that we will get a sample mean of this value when the fact this was the population mean, when the fact the population mean is 50, and then because the sample mean is very far from the population mean, so that indicates there's a need to reject the null hypothesis stated as mu equal to 50. So we reject the null hypothesis and we accept the alternative hypothesis. So the test statistic and the role of critical value. So now we look at the role of critical values in hypothesis testing. If the sample mean is close to the stated population mean, the null hypothesis is not rejected. So if sample mean is close to the stated population mean, we are not going to reject the null hypothesis. If the sample mean is far from the stated population mean, the null hypothesis is rejected. So the question is, how far is far enough to reject the null hypothesis? So we want to know how far, yeah, before we reject, how far the difference, how big is the difference should be before we reject the null hypothesis. So this is our null hypothesis, mu equal to 50, mu not equal to 50, just for example. So then we collect a sample and calculate the sample mean, which is equal to 20. The critical value of a test creates a line in the sand. So we need to know this. We have to answer how far is far enough. So to answer this, to help us to answer this question, so we need to calculate the critical value. The critical value of a test statistics that will help us to decide whether to reject or to accept the null hypothesis. So the critical value will help us to answer the question of how far is far enough. So here is our critical value. So we can calculate this critical value based on our significant level. I will show you how to do it later. So this is our critical value to the left and to the right. So here we have a situation where we have two critical values. At the center is the mean of the population. So between these two critical values, we have a region of non-rejection of the null. And to the left, we have another area, small area, that represent the region of rejection of null. And also to the right, we also have a similar size of area to represent the region of rejection for the null hypothesis. So then based on this critical value, we 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 know when to reject and when to accept the null hypothesis. So that is the role of critical value. Critical value considered as the border between rejection area and non-rejection area. Let's take a look at the risk in decision making using hypothesis testing. So there are two types of error. So when we make a decision, our decision can be correct, can be wrong. So there is no guarantee that we always make a correct decision. So here we have some kind of risk when we make decision in hypothesis testing. What are the decision I'm talking about? We are talking about whether to reject or to accept the null hypothesis. So type 1 error is when we reject a true null hypothesis. So if when the null hypothesis is true, but we reject it, so that is considered as a wrong decision. So that wrong decision is known as type 1 error. Type 1 error reject a true null hypothesis. Type 1 error also known as false alarm. False alarm. The probability of type 1 error is denoted by alpha. And alpha is also called level of significance of the test. So alpha also represents the level of significance of the test and also represent type 1 error. And alpha is set by researcher in advance. So usually we use a small alpha such as 0.05, 5%, 1%, or 10%. 0.05 represent 5% error, 0.01 represent 1% error, and 0.1 represent 10% error. So then the other type of error is called type 2 error. It's happened when we fail to reject a false null hypothesis. A failure to reject a false null hypothesis is called type 1 error, type 2 error. Type 2 error represents a missed opportunity. Missed opportunity refers to we have the opportunity to reject the null, but we fail to reject. So that's why it is called missed opportunity. There's opportunity to reject, but we do not reject. The probability of type 2 error is denoted by beta, symbol beta. Okay, here we look at the possible error in hypothesis test decision making. So this is actually another way of looking at type 1 and type 2 error. So we have a decision to make whether to not to reject. Do not reject means we accept the null, or reject, whether we want to accept or to reject. And then this is the actual situation where the null is true and the null is false. We are set to make a correct decision when we do not reject a true null. When actual situation, the null is true and we do not reject the null. So we have made a correct decision. Confidence is equal to 1 minus alpha. Then we have type 1 error. Type 1 error occurs when we reject a true null hypothesis. The null hypothesis in actual situation is true, but we make a mistake to reject the null hypothesis. So then we have committed type 1 error. So type 1 error, the probability of committing type 1 error is equal to alpha. So here another situation where we make correct decision, where the null hypothesis is false and we reject. So we reject a, a false null hypothesis. Then this is considered as correct decision. Then this is the power of the test. Power of the test is equal to 1 minus beta. 1 minus alpha is the confidence. Type 2 error occurs when we fail to reject a false null hypothesis. So the hypothesis null is false, but we do not reject. So type 2 error. So probability of committing type 2 error is equal to beta. And it is also known as a missed opportunity, and type 1 error again is a false alarm. So here are some terminology that we can use. 1 minus alpha is known as confidence coefficient. 1 minus alpha is known as confidence coefficient. It represents the probability of not rejecting null hypothesis when it is true. And we have a confidence level of hypothesis test when we multiply 1 minus alpha times 100%. We create confidence levels. And then the power of statistical test is calculated using 1 minus beta, and it is the probability of rejecting null hypothesis when it is false. Type 1 and type 2 error relationship. Type 1 and type 2 errors cannot happen at the same time because they are mutually exclusive situation. So type 1 error, type 2 errors cannot happen at the same time. If you have committed type 1 error, then you do not commit type 2 error. Type 1 error can only occur if null hypothesis is true. So we reject it. And remember, type 1 error is where we reject a true null hypothesis. Type 2 error can only occurs if null hypothesis is false. The null hypothesis is false, but we fail to reject. If type 1 error probability is alpha increases, then type 2 error probability beta decreases. So this is a relationship between type 1 error, type 2 error. It's because type 1 error and type 2 error are related. Increase alpha, beta will decreases. If you decrease alpha, beta will increase. So that is the relationship between type 1 error and type 2 error. Level of significance and the rejection region. So here, let's say we have null hypothesis and alternate hypothesis written as mu equal to 30 and mu not equal to 30. And we use level of significance alpha. And based on this information, we can draw this diagram, normal distribution diagram, where the center of the distribution is equal to 30, and we have a situation where we have two rejection area. How do we know we have a two rejection area? Because the alternate hypothesis uses not equal, symbol not equal to. Whenever we use symbol not equal to, that tells us we have a situation, two rejection area. Two, we call it two tail test. Yeah, two tail test. We have two rejection area to the left, one to the left, one to the right. And then this area, the rejection area, the size of the rejection area depends on our level of significance. So since we have alpha to represent level of significance and we have two rejection area, so this area must to calculate this area, we have to divide the alpha into two portion. Alpha divided by 2 here, this part, and also alpha divided by 2 to the left. So this area, left area and the right area should be equal. When we add this, the left area and the right area, it should be equal to level of significance. And this is a two-tailed test because, as I mentioned just now, we use symbol not equal to for our alternative hypothesis. And these are our critical values. To get these critical values, it depends on the alpha level. Okay. So we can get these critical values from the table based on the alpha levels. Divide by 2, we calculate critical values using a table, the appropriate table. In this case, maybe we can use the Z table. So these two areas represent the rejection area. That is the end of part 1. Thank you very much.